Welcome to Curiosity Meets the Past, a podcast for curious minds who love learning about the past. I'm Dr. Smitty Nathan, and I'm an archaeologist and your host. In this episode, I'm speaking with physicist Dr. Sabetta Matsumoto. Part of her research explores the geometric and mechanical properties of various textile techniques. I first met Sabetta when we attended a festival put on by the Independent Media Initiative. A portion of the festival attendees were fellow educators who wanted to help people learn about their fields by creating content that both informs and engages broader audiences. Sabetta and I connected on a lot of levels, including our shared fascination with past textiles and the techniques used to make them. In our conversation, we explore the physics behind past textile techniques and what they reveal about us as humans. Now, if your physics knowledge is a bit rusty or you don't know how to knit or crochet, don't worry. We make sure to walk you through the key physics and fiber arts terminology that we use in this episode. We also talk about a pretty cool historical sock. Sabetta starts us off with the surprising story of the moment she realized she could merge her two interests into an interdisciplinary field of study.
So for me, my mom was a really big influence in my life. So she was always a textile artist. And so growing up, we did a lot of stuff together. Like we would sew clothes, do knitting. I think for me growing up, like the idea of textiles was just a really integral part of my childhood and adolescence. And then I guess it was always my hobby because I really enjoy anything artsy. And then I went to college and did a degree in physics and, was just kind of happily going along doing physics stuff. And then one day, my office mate had a project on something that I hadn't heard of. It's this thing called the hyperbolic plane. And I was curious, so I looked it up. And like one of the first things that I came across were people crocheting. So there's this crocheted coral reefs project that is sort of at the intersection of math, biology, and conservation, where they were crocheting these mathematical objects that look like the corals in a reef and making these really intricate sort of coral reefs on a room scale kind of installation. And they were using that to raise money for reef conservation. And this just really blew my mind because it was the first time when I was like, math and my hobby, they were the same thing. And so I was really excited to be able to think about that in like a more serious way. So I know there were people doing math in textiles, but there weren't that many people doing physics in textiles. So I kind of wanted to blend the almost materials, science, mechanics lean of what my PhD and postdocs were in with how I interact with textiles.
That is so cool. And I love that vivid example. And I know part of your work focuses on what's happening inside textiles. And is there more to the story there of what got you interested in that approach?
Yeah, that's a great question. So when I was growing up, my mom had some sort of encyclopedic knowledge of everything textile and would always sort of know things like, oh, this has this hand and this has this drape. And there were all of these really subtle behaviors that different kinds of fabrics had that would always go into how she described them. And so there was this kind of word of mouth way of learning intuition, but there isn't really a lot that's sort of quantified, like why does something drape better or why is something stretchier or anything like that. So I was really interested in sort of taking this communal knowledge that people have been developing over hundreds, if not thousands of years, and trying to come up with a way of thinking about dissecting that using physics language.
That's amazing. And honestly, you're speaking the language of archaeologists when you're talking about shared practices and especially knowledge transfer in the material record. But I can imagine that this is interdisciplinary work. So you're bridging physics and textiles. And while it's incredibly worthwhile, in my own research, I really appreciated working in an interdisciplinary fashion between archaeology, geophysics, and the botanical record. It can also be quite challenging because you have to convince sometimes other parties, even in your own field, that it's a worthwhile pursuit. So I'm wondering, what was the response from your fellow physicists about this work? And did you have to do kind of any convincing or proving that it was worth doing?
Yeah, being interdisciplinary is such an important part of science right now. I think there's so many more ideas we can get by looking at people who have complementary knowledge to ours. And that is starting to become more mainstream. And I think the thing that maybe was the most interesting kind of view that I had into this was when I was interviewing for jobs, where I think I got a lot of interviews from people who were just curious, but were a little bit afraid of what this meant. So I think that was a place where I think I kind of came up against this like, is it serious? Is it not serious? I guess the place I'm currently at does have like quite a long history of having interdisciplinary pursuits, both in our department and just in our university in general. So I'm at an engineering school. So anything that kind of involves making stuff or building stuff tends to fit in. I think I didn't have this problem as much because I think I'm a very much like march to the beat of my own drum kind of person. But I think people who are in my group or like collaborators, things like that, who may have come from slightly more, let's say, traditional physics pursuits, it was a little hard to convince them that, like, convince other people that what they were doing was as important and as valuable as like more traditional practices. And I think that doesn't necessarily come from it being interdisciplinary as much as it comes from it being women's work. And so that puts a stigma on different kinds of approaches to what qualifies as science.
That totally makes sense. And, we have some videos on the fiber arts and fiber arts products. And as we were researching this history, yes, a lot of people who identify as women are participating in this craft, but it's also a wider body of people than we thought. I remember in one video, people were mentioning, like, hey, why didn't you mention the medieval guilds, which were primarily by men? And I was like, that's a good point. And so, even as we examine and re examine the archaeological record, we're learning new things. So, I really appreciate hearing your perspective. And let's transition a little bit to the archaeological. One knit object or textile object that we've both encountered or talked about in different ways are socks. And I was wondering if you had a sock example you could share with us and kind of what we can learn by looking at the physics behind it.
Absolutely. So there are sadly very few truly ancient socks, at least from the knitting tradition. It looks like most of the extant examples come from, I guess, sort of Egypt and the Middle East and are clearly done in sort of an Arabic tradition. But I think the one thing I want to point out, in particular with the sock example that I've chosen, is that these are incredibly sophisticated, and there's virtually no difference between what we would do in today's modern knitting than what these examples are. So I think that raises a really interesting question of how did knitting evolve if what we have in the archaeological record is basically just modern knitting. So I should say that I personally come from a hand knitting tradition, which is distinct from the modern machine knitting tradition and the textile engineering traditions. So, for knitters out there, I will be looking at things from the point of view of the modern hand knitting tradition. So this is the particular sock that I've been personally fascinated by. It's from the George Washington Museum Textiles collection, and it's from the 12th century, and they're guessing it's from around Egypt. And this sock is absolutely gorgeous for so many reasons. The patterning on it is incredibly intricate. And this type of color work is something that we see in a lot of modern knitted garments and patterns. So this sock has a lot of incredible details to it. And one thing that is particularly interesting from a physics point of view is what we would call shaping stitches. And so what we can see is this sock clearly has a rounded toe. It has a heel, and there's some specific stitches used along here to create the shape of the heel. And also the width of the sock changes as it goes up the calf. And the way that they achieve these is similar to how physicists study objects in what's called crystallography. So most knitting is created with these V-shaped stitches. So here there's three V's stacked on top of one another to create this light blue band. And then there's a lot of V's next to each other. So looking at each of these V's, we could define something that's called a lattice. So it's sort of a set of rectangles that would sort of connect the center of each of the stitches together, and that would sort of define every time you have like an intersection of the rectangles, that's where you would expect a stitch to be. And there's a couple of things that you can do to disrupt what that rectangular order would be. And this sock takes advantage of a lot of different kinds of those things that we see in the physics of crystals. One of those examples is right here. So we have one V right here. And if we move up a stitch, up a row, we have two V's that are trying to occupy this space where we would expect one V to go. And so this is one thing that they would use to create the shaping around the calf. And this particular type of what we would in physics call a defect is a place where we've inserted a whole new row of crystals up here. So we've sort of widened the calf just a little bit at this point. And we can look throughout the entire sock and see that this has happened in many places. So there's one place over here where this has happened. There's a place over here where this has happened. I'm sure there's plenty other on screen, but those are just what I'm seeing with my eyes right now. The other place that's really fascinating is the heel. And this uses a technique that we use in a lot of modern heels. And from the knitting point of view, this is called a short row. And from the physics point of view, we would call this a disclination, which is a big word that means that the orientation, so the direction that my rectangles are pointing in, goes through a change. So they're oriented this way here, and then oriented this way up here. And it does that through a series of special stitches throughout this heel.
Wow, that is absolutely fascinating. And hearing you speak, it just really reminds me of basically translation. Sometimes we're trying to translate ancient texts into modern ones, but, working in an interdisciplinary fashion like you are, we're translating what we're seeing in the knitting world to what's happening in the physics world, or I guess the physics worldview of understanding things. Was there a particular connection, and it doesn't have to be about socks, that made you really excited when you were like, hey, I see that these things are connected?
So it wasn't initially about socks, but looking at these two structures, often we would see them in other places. So we do see like heels of socks, but we would also see like how you would shape the bust of a sweater, something like that. So I guess I grew up in the Y2K era where everything was skin tight and cropped. So learning how to make stuff that like fitted perfectly was definitely something that was interesting to my fashion tastes at the time. Maybe not so much now, but so those were things that I learned to do because of that. And so translating those over into this language of crystallography, which is something that came up during my PhD, was something that really caught my attention. And so that was like a big hook for me.
Gotcha. Thank you for that. And would you mind briefly explaining crystallography for those of us who might not be as familiar with that term or field?
Yeah, so crystallography it's a pretty broad term and it encompasses a lot of fields, including geology, chemistry, physics. I'm sure there's plenty of others. And so basically, when you are looking at a mineral that's a crystal, the atoms in a crystal arrange in a really regular pattern. The way that they stack together forms what are called symmetries. So a symmetry can be something where you're like, I move this one unit to the left and it looks the same. Or I can rotate everything by 60 degrees and it looks the same. And there are several other more complex symmetries, but basically we're looking at how to understand the microscopics of a larger object that has very repeated units in it from the point of view of looking at symmetries. And so one place this came up very famously in the sort of physics meets biology meets chemistry era is the Rosalind Franklin images of DNA. So she used a type of crystallography that's called X-ray crystallography, which uses X-rays to image those symmetries. And she was able to see that, well, actually, there's a rotation in the DNA, which means that it had to form a helix.
That's absolutely fascinating. And thank you for giving us that breakdown of crystallography. I was not as familiar with the field. And if our listeners weren't as well, I'm sure they really appreciate hearing that breakdown and those examples. Now, to go back to textiles, I'm curious to talk a bit more about knitting and the fact that, we've had offline conversations that talk about some of the properties of knitting as a technique, and one of them being its ability to stretch. And I'm curious if you can talk a bit more about the relationship between stretching and textiles and physics, and if you have any other examples you'd like to share.
So, stretchability is something that's absolutely crucial to textiles and how we use them as garments. We take it for granted now because we have all sorts of synthetic fibers like elastane, which is the chemical name for things that make up lycra and spandex. We have polyesters and acrylics that are petrochemicals that mimic natural fibers. But back hundreds and thousands of years ago, having woven fabric doesn't provide any type of like elasticity or stretchability. And for garments, getting something over your head where your head is much larger than your neck, or having something that goes over your hands but stays on your wrists are really useful for just functionality of our clothing. And things like buttons and ties and other closures are things that do this. But having something that's an integral part of the fabric makes the fabric so much more functional. And I have some examples of different knits here. And this is sort of one of the first projects that I knew that I had to do as a physicist is to sort of understand why different knit stitches have different types of stretchability. So these are all made with the same yarn, and this yarn If I pull on it, it doesn't stretch very much. It might stretch 1 or 2%, and that's just like wool slipping past itself. And so here's the fabric, and this is called stockinette fabric. This is what makes up t-shirts, makes up socks, underwear. This is, everyone watching this. Okay, maybe not everyone, but are most people watching or listening to this probably are wearing something made out of this material. And this is great because it is quite stretchy. You can sort of see me pulling on it, and I'm going to try to pull on this with like approximately the same amount of force for each one so you can see how far it stretches. And so it stretches a little bit differently in different directions. Like it's more stretchable, so we would call it softer in this direction, and it's less stretchable, so we would call it stiffer in this direction. And we can do different things with different stitches. So here's an example of what we would call ribbing, and ribbing is made with alternating knit stitches and purl stitches. And this one, if I pull it with like the same amount of force, it extends so much more. So this extends like, I guess, if we quantified it, it stretches about 10 times more in this direction for the same amount of force. And then it's pretty similar, maybe a little softer in this direction. And so these are different types of stitches that get used all the time in different garments. So that first example I showed you would often form like the body of a sweater, but this type of ribbing is something that would form the cuffs and collars. So it's much easier for this to stretch over a head, but it snaps back around the neck. And the same with around a wrist. And so in physics, we would call this a metamaterial. And a metamaterial is where we would take an object or a material that has a certain set of properties. Like here, our yarn stretches only 10%. But then we do something to it. We sort of give it some repeated geometric pattern. So here, those would be our stitches. And something about that patterning of this other material kind of unlocks its ability to have new properties. In this case, this material is going to be many, many, many times stretchier than her original material that's just the yarn.
Those examples were absolutely fascinating. And I'm wondering if there's another historical textile technique example that you can share with us that also illustrates some type of stretch.
So one of the most fascinating examples is a technique called smocking. And this is an embroidery technique that appears to have been in use in the Middle Ages. And this is an embroidery technique where you take regular woven fabric and you take stitches that basically make a little pleat in the fabric, and you sort of offset those pleats in certain ways. So it acts almost like an accordion when you stretch on it. And this is really fascinating because this is one of the only embroidery techniques that was accessible to and used by peasants because it had so much functionality directly in translating regular garments into garments that could be used in multiple contexts. So, for example, when I was a baby, my mom made me a smocked dress. So she did hand smocking and embroidery on it. But she basically made this enormous hem in it so that she could just keep letting out the hem as I grew taller, because with smocking, it's so stretchy that as I grew wider, it would just accommodate that. And then the hem she could just modify as I got taller. So something like this could make one garment usable for a child across a large portion of their lives, or be easy to switch from child to child. And so those are places where the cost of having to reclothe them, I guess as modern parents know, is incredibly expensive when your kid goes through a growth spurt. But, in prior times when we can't just go to Walmart or something like that to pick up new clothing, having to make a whole new garment might be too costly or too time consuming for it to be worthwhile for a family. So having things that are flexible can have a lot more utility for one garment.
I love hearing that, especially as a parent. I feel like I will buy one garment and then they immediately don't fit them anymore. But then, we also have some garments that almost feel magical because they've used them for 2 years and in the span of young children, that is a long time. And it honestly got me thinking, okay, what is inherent about this garment that allows it to be used for a bit longer? And I'm wondering, as a physicist and studying the physics of past textile techniques, what do you think we can learn about people from the past?
One thing I really like about physics is that it can ask very different questions about utility by studying what is sort of inherent to the properties of materials. So I think it's really fascinating to be able to take past techniques and then recreate them in the modern era to try to untangle what is special about those different techniques. I also find it really fascinating, particularly in terms of things like textiles, which are very much handed down, and different cultures will come up with their own techniques and things that work for them. So I think it's really fascinating to be able to kind of look at those in sort of the context of what utility they might have gotten out of them. And even if that utility is just aesthetics, I think that's equally valid.
I totally agree. I think aesthetics and what we find beautiful could be a whole other podcast topic for sure. And to wrap us up here, I'm curious, what do you hope listeners take away about the physics of past textile techniques?
I guess I hope that people find a new way to look at their everyday objects and just ask questions about the world around them because it's endlessly fascinating, whether it's the t-shirt that I'm wearing, whether it is a piece of pottery, whether it is a book. So I will challenge everyone to find something unique in the everyday today and think about that.
One of my biggest takeaways from this conversation is that pursuing interdisciplinary work not only leads to richer science, but it's also really engaging for the researcher and broader audiences. If you'd like to learn more about Sabetta's work, you can check out her YouTube channel, Sabetta Talks Math, and her research group's website. You'll find those links in the show notes, along with a link to a full transcript of this episode. And if you're curious to dig deeper and learn about some of Sabetta's past and current textile projects, she shares that and more in a Patreon exclusive video. Our Patreon is free to join and gives you access to all of our extra content. If you'd like to support the podcast monetarily, we'd of course appreciate that too. Thanks so much for listening and cultivating your curiosity with us. We'll see you soon.